Hello everyone, and welcome to today's chem lesson. Today we are going to spend a little bit of time talking about the kinetic molecular theory, which is a set of rules that talks about the way gases should behave. Now, we spent a little bit of time in a previous video looking at the idea of particles of a solid, liquid, and a gas, and how they behave and how they're a little different. Solid particles are packed together in nice orderly rows and columns. They vibrate slightly, but otherwise don't have a lot of movement. When you melt a solid and get a liquid, you spread the particles out a little bit, and you give them the ability to move around each other, to go freely in front of or behind the particles that they need to go in front of or behind. Right? This free motion allows liquids to take the shape of their container and not stay in a rigid pattern like a solid. When you take a liquid and you boil it to get a gas, you spread out the particles very far apart and you speed them up so that they're going very fast. And they move around the entire container, right? They fill their container, moving in straight lines until they hit a wall of the container and bounce off, or until they hit another particle and bounce off. Now, we focused on solid and liquid in the previous unit, but here now we're focusing entirely on gases and the way that they behave. So the first thing, what I was just discussing, is the idea that gases move in random, continuous, straight line motion. Right, moving in a straight line until they hit something and then bouncing off. But there are more little rules to gases than just that. When two gas particles collide, in this small comic strip we'll draw here, when two gas particles collide, energy is transferred between them. And when they bounce away, the total energy should be the same as it was before they collided. So if they start with 7 joules and 3 joules for a total of 10 joules, when they collide and energy gets transferred, when they leave, energy should be transferred but not a different total. Right here we have 6 and 4, which is still a total of 10 joules. So 10 joules before and after their collision. A collision like this, a collision where the total energy remains the same, is called an elastic collision. Right? Energy is transferred, but no energy is lost. The third piece of the kinetic molecular theory talks about the volume of gas particles and how they are negligible. Now, the word negligible is a word that means it can be rounded down to 0. And so if I look at this box, 10 centimeters by 10 centimeters by 20 centimeters has a total volume of 2,000 centimeters cubed. If I say that this box has gas in it, that does not change the volume of space inside this box. Right? Because the gas particles take up so little space inside this box that we can say they take up 0 space. Right? Volume of gas particles can be rounded down to 0 when you're looking at how they compare to any container. Right? We don't have to subtract the 0.02 centimeters cubed, which is being very generous, that the gas takes up. Right? We can say this box is 2,000 centimeters cubed empty, 2,000 centimeters cubed with gas in it. The gas takes up no space. And the last piece of the kinetic molecular theory is the idea that gases have no force of attraction for each other. If I have two gas particles that are not going to collide, but that are going to come very close to each other, if they had forces of attraction between them, they would be pulled kind of towards each other. And instead of following this straight path past each other without caring, they would be tilted just a little bit towards the other particle. But gas particles we're going to assume that they have no forces of attraction for each other, and so we're going to ignore these blue lines and say that the red lines are the ones that the gas particles will follow. All right, a straight line until it hits something. Now, gases that follow the kinetic molecular theory are called ideal gases. Right? An ideal gas is a gas that follows all four of these laws completely. But the fact of the matter is that there are no gases on this planet that follow the kinetic molecular theory perfectly. Gases on Earth have attraction for each other. They take up space. They have volume. Collisions on Earth aren't always elastic. Oftentimes they are inelastic, and energy is lost in some way. And so we are going to treat gases as if they are ideal gases, but we are going to recognize the fact that we are assuming that. Right? In reality, gases are real. The two closest gases that we have on Earth to ideal gases are helium and hydrogen, for a reason that we're going to talk about on the next slide. Right? But all of our gases, everything you've ever interacted with, has been a real gas and not an ideal gas. When we look at real gases, like I said, they have volume, they have attraction for each other. Their collisions aren't always elastic, and so they don't follow the kinetic molecular theory perfectly. We can make gases behave more ideal by spreading out the particles and by giving the particles a small relative volume. This combination is what makes helium and hydrogen the most like ideal gases. They have the furthest particles and they have the smallest volume. We can make real gases behave more like ideal gases by increasing the temperature and decreasing the pressure. These conditions are going to help the particles spread out and take up as little space as possible. Right? Increasing the temperature and decreasing the pressure is going to make real gases behave more like ideal gases. Now I hear it in your voice. You say, Mr. M, why are we going to talk about ideal gases when all of the things that we've interacted with are real gases? What's the point of learning about ideal gases when the air around me, the air in this balloon, the air in my lungs are all real gases? And the reasoning behind talking about ideal gases is because it lets us learn the basics of how gases work. If we want to solve problems and do calculations for real gases, the formulas, the math involved, the concepts involved become much, much more difficult. And at the end of the day, when we're solving a problem for a real gas versus an ideal gas, if the answer for an ideal gas is 5 liters, the same question for a real gas would be 4.999986 liters. So it really doesn't make a big difference mathematically to talk about ideal gases versus real gases, but it saves us a lot of headache. It saves us a lot of things we need to check for. And here, we're looking only for the basics. We're not going to get into super depth on a lot of these topics. And so we're going to recognize that if you're working at NASA or you're building an airplane, then real gases are important. But when we're talking about the deflation of a balloon, we can talk about ideal gases and kind of round out the things that make it difficult. In our next video, we're going to talk about the formulas that we're going to use, some of the things we're going to look at to compare volume, temperature, and pressure of ideal gases. But for now, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.